Picture this: a world so vast and strange, its rings alone stretch wide enough to fit 6 Earths side by side. Saturn, the crown jewel of our solar system, has mesmerized humanity for centuries, from ancient stargazers who saw it as a wandering god to modern astronomers uncovering its mind-bending secrets. But here's the thing: those dazzling rings, they're just the beginning. Beneath that golden glow lies a trove of mysteries so bizarre, they defy everything we thought we knew about planets. Imagine a place where diamonds rain from the sky, where a storm rages in the shape of a perfect hexagon, one so massive it could swallow our entire planet whole. Saturn isn't just another dot in the night sky. It's a cosmic carnival of the unexpected, a laboratory of the impossible. And yet, for all its grandeur, most of its strangest quirks remain hidden, tucked away in data from distant probes or buried in the fine print of scientific papers. That's where this journey begins. Today, we're pulling back the curtain on Saturn's most jaw-dropping secrets, 30 discoveries that'll make you question reality itself. From moons that could harbor alien life to magnetic fields that twist space-time, we're diving deep into the enigmas that make this planet a true outlier. So buckle up, whether you're a space enthusiast or just love a good mystery. What you're about to discover will leave you seeing Saturn and our universe in a whole new light. One of the most mind-bending mysteries of Saturn isn't in its iconic rings. It's at the very top of the planet. Picture a hurricane, but not just any hurricane. This one is shaped like a near-perfect hexagon, a 6-sided geometric wonder so precise it looks almost artificial. Stretching wider than 2 Earths stacked side by side, this swirling maelstrom has raged non-stop at Saturn's North Pole for at least 4 decades, maybe even centuries. The first hints of this freakish storm came from Voyager in the early 1980s, but its details remained fuzzy until Cassini arrived decades later. What the probe saw stunned scientists. Unlike the chaotic cyclones we see on other planets, this hexagon is unnervingly stable, with razor-sharp edges maintaining their shape like a cosmic honeycomb carved into Saturn's atmosphere. Even more bizarre, the entire structure rotates in sync with the planet's deep interior, completing one full rotation roughly every 10 hours and 30 minutes like a colossal invisible gear. So how does something this strange even exist? Theories range from wild to downright otherworldly. Some scientists suggest deep-rooted vortices, massive spinning columns of gas, act like invisible walls, shepherding the jet stream into this geometric pattern. Others point to atmospheric waves, where differences in wind speeds create standing waves that lock the hexagon in place. Then there's the mind-boggling idea that Saturn's own rotation, combined with complex fluid dynamics, could naturally generate such a shape. But here's what truly chills the spine. Earth's hurricanes dissipate in days or weeks. Jupiter's great red spot, while ancient, is still just a swirling blob. Saturn's hexagon, it defies every rule, a storm that outlasts civilizations, a puzzle whispering that we've barely scratched the surface of how planetary atmospheres really work. Just when you thought Saturn couldn't get any weirder, its rings throw another curveball, ghostly streaks that materialize out of nowhere, only to vanish like cosmic illusions. These are the spokes, eerie, shadowy fingers stretching radially across the rings, as if some unseen hand dragged a giant brush through the dust. First spotted by Voyager in the 1980s, they've confounded scientists ever since, appearing and disappearing with no obvious pattern, sometimes lingering for hours, other times fading in minutes. What makes these features so baffling is their defiance of expectations. Saturn's rings are made of countless chunks of ice, from tiny grains to boulders, all orbiting in orderly, predictable paths. Yet these spokes slice across that motion, breaking the rules. Imagine a carousel spinning smoothly, then suddenly, streaks of shadow radiate outward, ignoring the rotation entirely. The best guess, electrically charged dust particles levitating above the ring plane, caught in a tug of war between Saturn's magnetic field and the Sun's radiation. Here's where it gets wild. These spokes seem tied to Saturn's seasons, appearing more frequently when the planet tilts its ring's edge onto the Sun. One theory suggests that during these periods, sunlight charges the dust, causing it to rise like iron filings drawn to a magnet. But there's a twist. Some observations hint that the spokes might also be linked to massive lightning storms in Saturn's atmosphere, thousands of miles below. Could invisible electromagnetic forces be bridging that gap, somehow teleporting energy upward? The real kicker, even Cassini, which spent 13 years studying Saturn up close, couldn't crack the spoke code. They'd vanish before instruments could fully analyze them, leaving behind more questions than answers. It's a reminder that for all our technology, some cosmic secrets still dance just beyond our grasp, fleeting, enigmatic, and utterly mesmerizing. Saturn spins so fast it flattens itself, a fact that sounds like science fiction until you realize this gas giant completes a full rotation in just about 10.5 hours. But here's the catch. Pinning down Saturn's exact day length is like trying to measure smoke. Unlike rocky planets with solid surfaces, Saturn's a swirling ball of gas with no mountains or craters to track. For decades, astronomers relied on rhythmic radio bursts from its magnetic field, assuming those pulses mirrored the planet's inner rotation. Then Cassini delivered a bombshell. Saturn's day isn't just hard to measure, it's getting shorter. The mystery starts with Saturn's magnetic field, which behaves unlike any other in the solar system. Most planets, including Earth, have magnetic poles roughly aligned with their rotational axis. Saturn's, though, is almost perfectly symmetrical, hiding any wobble that might reveal its spin. Early estimates based on Voyager data in the 1980s suggested a day lasted 10 hours, 39 minutes. But when Cassini listened decades later, those radio pulses had sped up, pointing to a day nearly 8 minutes shorter. At first, scientists thought it was an observational error until they realized the planet itself was changing. The leading theory, Saturn's immense winds, some blasting at over 1,000 miles per hour, might be dragging its magnetic field along like an invisible tether, slowing it down over time. But deeper still, there's the enigma of Saturn's interior. Beneath those dazzling cloud tops, hydrogen compresses into a bizarre metallic state, swirling around a dense core. Some researchers argue that this metallic hydrogen layer could be decoupling from the outer atmosphere, like two gears spinning at different speeds, warping the magnetic field's rhythm. Others speculate that helium rain, yes, actual droplets of helium falling through the hydrogen sea, might be altering the planet's internal dynamics, subtly tweaking its rotation. The implications are staggering. If Saturn's day is truly shrinking, it challenges our fundamental models of how gas giants age and evolve. Faster rotation could intensify its already violent storms, stretch its polar vortices, even reshape its iconic rings over millennia. But the real lesson here is humbling. Even a planet as studied as Saturn keeps its deepest secrets locked away, reminding us that the cosmos always has another card up its sleeve. Saturn's auroras don't just dance, they dominate. Unlike Earth's shimmering northern lights, these celestial spectacles are colossal, stretching thousands of miles across the planet's poles and glowing with an intensity that outshines anything in our solar system. Imagine curtains of light so vast they could wrap around Earth multiple times, pulsing with energy equivalent to thousands of nuclear detonations per second. And here's the kicker, they're not just pretty lights. These auroras are cosmic fingerprints, revealing secrets about Saturn's magnetic personality that scientists are still scrambling to decode. What powers this otherworldly display? It's a tug of war between Saturn's magnetosphere, a protective bubble of magnetic fields, and the solar wind, a relentless stream of charged particles blasted outward by the Sun. When these particles collide with gases in Saturn's upper atmosphere, They ignite auroras in hues of ultraviolet and pink, invisible to our eyes but dazzling to space telescopes. But Saturn throws a curveball. Its auroras don't always behave like Earth's. Sometimes they pulse rhythmically, flaring in perfect sync with the planet's mysterious radio emissions, a phenomenon nicknamed the Saturn kilometric radiation. It's as if the planet itself is sending out cosmic Morse code. The strangest part, these pulses don't match Saturn's rotation. On Earth, auroras flicker randomly, shaped by solar storms. But Saturn seem to march to their own drum, with some scientists suggesting they're tied to geysers erupting from the moon Enceladus. Plumes of water vapor, torn apart and ionized, might be funneled along magnetic field lines, literally raining charged particles onto Saturn's poles. Others argue the planet's own weather is to blame. Massive storms deep in its atmosphere could be warping the magnetic field, creating surges that ignite the auroras like a celestial light switch. Yet for all their grandeur, these light shows are fleeting. Cassini witnessed auroras suddenly brightening, then vanishing within hours, a volatility that defies prediction. It's a humbling reminder, even in our cosmic backyard, the universe keeps its most dazzling performances just out of reach, leaving us to wonder what other secrets pulse in the dark. Buried beneath Saturn's golden haze lies a tempest so fierce, it could rewrite the book on planetary weather. Meet the Dragon Storm, a monster of swirling gases and electrified chaos, where lightning bolts erupt with a force thousands of times stronger than anything on Earth. This isn't just another thunderstorm, it's a leviathan that can rage for months, lighting up Saturn's radio waves like a cosmic distress signal. And the wildest part, we wouldn't even know it existed if not for the eerie crackles and pops it broadcasts across space. The Dragon Storm first announced itself in 2004, when Cassini's radio antennas picked up bizarre bursts of static, each one a lightning strike so powerful it outshone all of Earth's thunderstorms combined. Unlike our fleeting summer storms, this beast doesn't fizzle out. It hibernates, disappearing for years before reigniting in the same spot, as if some unseen furnace beneath Saturn's clouds keeps stoking its fury. Scientists tracked its movements by triangulating those radio screams, painting a picture of a storm so vast it could swallow continents whole. But here's where it gets even stranger. These megastorms aren't just light shows, they're cosmic chemists. Every bolt superheats the atmosphere, transforming simple molecules like methane into complex organic compounds. Some researchers believe these reactions could seed Saturn's upper layers with precursors to life's building blocks, raining down bizarre chemistry we've only seen in lab experiments. And the Dragon Storm isn't alone. Saturn's atmosphere crackles with lesser storms, each contributing to a global electrical circuit that may help explain why the planet's auroras pulse with such unnatural precision. The real mystery, though, is what fuels these storms in the first place. On Earth, thunderstorms feed on warm, moist air rising from oceans. Saturn has no oceans, just an abyss of hydrogen and helium. One theory suggests that droplets of helium, condensing like rain deep inside the planet, release latent heat as they fall, creating colossal updrafts. Others point to Saturn's internal heat, left over from its formation, bubbling up through layers of metallic hydrogen like a pot boiling over. Whatever the cause, the Dragon Storm stands as a defiant reminder. In Saturn's skies, the rules of weather as we know them don't just bend, they shatter. Saturn's rings aren't just static decorations, they're alive, shedding tiny ice particles in a silent downpour that's been drenching the planet for millennia. This is ring rain, a delicate but relentless shower of frozen material, tumbling from the rings into Saturn's atmosphere like cosmic confetti. For years, scientists suspected something was eroding the rings, but it wasn't until Cassini took its final, daring dives between the planet and its rings that the truth came into focus. The spacecraft's instruments detected dust-sized ice crystals, some no larger than a grain of sand, streaming downward at a rate that could fill an Olympic-sized swimming pool every half hour. What makes this phenomenon so startling is the scale. Saturn's rings stretch nearly 280,000 miles across, yet they're astonishingly thin, in some places barely 30 feet thick. The rain isn't uniform either. Cassini found its heaviest near the planet's equator, where gravity and magnetic fields conspire to tug material loose. And here's the twist: this rain isn't just water ice. Mixed in are organic compounds and silicates, remnants of asteroids and comets that strayed too close and were pulverized into the rings. It's a cocktail of primordial ingredients slowly seasoning Saturn's upper atmosphere. The real surprise: this rain isn't just falling, it's shaping the planet. As these particles plunge into Saturn's hydrogen-rich skies, they ionize, creating a layer of charged particles that interacts with the planet's magnetic field. Some scientists believe this could explain why Saturn's upper atmosphere is hotter than models predict, as the constant bombardment of ring material deposits energy like a slow-cooking cosmic oven. Others speculate that over millions of years, this rain could be draining the rings themselves, shortening their lifespan. But the most poetic revelation is how fleeting Saturn's iconic rings might be. If ring rain continues at its current rate, some estimates suggest the innermost rings could vanish in just 300 million years, a blink in cosmic time. It's a humbling thought. We're witnessing a celestial masterpiece in its final act, a reminder that even the grandest wonders of the universe are temporary. And yet, for now, every speck of ice that falls is a silent testament to the dynamism of our solar system, where even the most seemingly permanent features are in constant, beautiful flux. Among Saturn's menagerie of moons, none wears its strangeness as boldly as Iapetus, a cosmic yin-yang, with one side gleaming like fresh snow and the other darker than charcoal. This two-faced moon doesn't just puzzle scientists, it defies logic. How can a single celestial body look like it's been split down the middle and dipped in opposing extremes? The answer lies in a combination of celestial theft, ancient eruptions, and a ridge so bizarre it looks like the seams of a walnut. The contrast is staggering. Iapetus's leading hemisphere, the side that faces forward as it orbits, reflects barely 5% of sunlight, making it one of the darkest surfaces in the solar system. Meanwhile, its trailing side bounces back over 60%, brighter than most fresh ice. Early astronomers, including Cassini himself, noticed this duality centuries ago, but it wasn't until spacecraft got close that the truth got even weirder. The dark material isn't native to Iapetus. It's cosmic litter, likely stolen from Phoebe, a distant, rouge-colored moon spewing dust as it drifts through Saturn's outskirts. Over eons, this debris spiraled inward, painting Iapetus's face like a slow-motion collision with a celestial paintbrush. But here's where the plot thickens. That dust doesn't just sit there, it triggers a feedback loop from hell. As the dark material absorbs sunlight, it warms the underlying ice, causing it to sublimate. The vapor then migrates to colder, brighter regions, freezing again and amplifying the contrast. It's a self-perpetuating cycle, turning Iapetus into a planetary-scale thermal engine. And then there's the ridge, stretching like a spine along the moon's equator. This mountainous wall towers up to 12 miles high and runs over 800 miles long, so precise it looks machined. Some theories suggest it's the frozen remains of a ring system that collapsed onto the surface eons ago. Others argue it's tectonic, a scar from when Iapetus's crust buckled as the moon's rotation slowed. The wildest idea, that it's evidence of a brief, catastrophic era when Iapetus spun so fast it nearly tore itself apart, leaving this ridge as its scream frozen in time. Iapetus doesn't just challenge our understanding of moons, it throws the rulebook out the airlock. A world where dust becomes art, where ice migrates like a living thing, and where mountains rise in perfect alignment with the stars. It's a reminder that even in Saturn's backyard, nature writes its own laws, and they're stranger than we dare imagine. Saturn doesn't just have moons, it has celestial sculptures, and none are more surreal than Atlas, a moon that looks like it was plucked straight from a 1950s sci-fi flick. This tiny world, barely 19 miles across, is shaped like a flying saucer, complete with a bulging equatorial ridge so pronounced it seems handcrafted. Orbiting just beyond the outer edge of Saturn's dazzling ring, Atlas isn't just a cosmic oddity. It's a window into the violent ballet of debris and gravity that shaped Saturn's rings and their shepherd moons. So how does a moon end up looking like a dinner plate? The answer lies in its location, dancing perilously close to the rings. Scientists believe Atlas formed from the same primordial material as the rings themselves, a leftover fragment that avoided being shredded by Saturn's tides. Over time, as it plowed through the sparse particles at the ring's edge, the moon acted like a celestial snowplow, gathering ice and dust around its equator. This material piled up, sculpting that bizarre ridge until the moon resembled a UFO mid-flight. But Atlas isn't just passively collecting debris, it's actively shaping the rings. Its gravity creates waves in the ring material, shepherding particles into sharp boundaries and preventing them from drifting outward. This delicate balance is why the outer edge of the ring appears so crisp, as if cut with a knife. The moon's orbit, perfectly synchronized with the ring's rotation, creates a gravitational resonance that locks both in place, a cosmic waltz that's lasted billions of years. Here's the twist: Atlas might not be alone in its strangeness. Other small moons, like Pan and Daphne's, sport similar equatorial ridges, suggesting this saucer shape is a common fate for moons born near the rings. Yet Atlas stands out for its symmetry, a perfect disk that challenges our assumptions about how celestial bodies form. Some researchers even speculate that its ridge isn't just built from ring debris. It could be the remnants of a shattered moon, a relic from a catastrophic collision that left behind this eerie, flying saucer silhouette. What makes Atlas truly mesmerizing isn't just its shape, but what it represents: a snapshot of cosmic evolution in action. It's a reminder that even the quietest corners of our solar system are laboratories of chaos and creation, where gravity and time sculpt worlds into forms far stranger than fiction. And as we peer closer, we're left wondering how many other secrets are hiding in plain sight, disguised as mere quirks in Saturn's celestial menagerie. Among Saturn's many moons, Hyperion stands out like a cosmic accident, a tumbling, misshapen blob that looks less like a celestial body and more like a piece of Swiss cheese left floating in space. This moon doesn't just orbit Saturn, it staggers, wobbling chaotically like a drunken top, its rotation so erratic that no 2 days, if you could stand on its surface, would ever look the same. But Hyperion's real shocker isn't its motion. It's what lies beneath that pockmarked, crater-riddled exterior, a labyrinth of void so vast this moon might be more empty space than solid matter. Close-up images from Cassini reveal a surface unlike anything else in the solar system. Hyperion's craters aren't just indentations, they're deep, honeycombed pits, their walls so thin and fragile that sunlight barely casts shadows inside them. The entire moon has the density of lightly packed snow, suggesting up to 60% of its volume could be nothing but gaps, a fragile, porous skeleton held together by little more than gravity and luck. Scientists call it a rubble pile moon, a loose collection of ice and rock that never fully coalesced into something sturdy. What created this cosmic sponge? The leading theory points to a violent past. Hyperion might be the sole survivor of a catastrophic collision, a fragment of a larger moon shattered eons ago. Without enough mass to pull itself into a spherical shape, it remained a jagged relic, its cavities preserving a record of impacts that would have obliterated a denser world. Every crater tells a story, not of destruction but of preservation, as Hyperion's weak gravity and porous structure absorb strikes like a cosmic shock absorber. But the real marvel is how this fragile moon defies time. Hyperion's chaotic rotation caused by Saturn's gravitational tug and its own irregular shape should have ripped it apart by now. Yet it persists, tumbling through space in a dance of instability that somehow works. Some researchers speculate its emptiness is its salvation. The gaps act as buffers, dissipating energy from collisions and tidal forces. Others wonder if Hyperion is a glimpse into the early solar system, a primordial time capsule showing how small bodies behaved before gravity sculpted them into order. One thing's certain, Hyperion doesn't play by the rules. While other moons march in predictable orbits, this cosmic oddball reminds us that chaos has its own beauty, and that sometimes the universe's most fascinating wonders are the ones that barely hold themselves together. Beneath the icy shell of Saturn's moon Enceladus, a secret ocean churns, and it's erupting into space. Imagine a world so cold its surface is frozen solid, yet so alive it shoots towering geysers of water vapor and ice crystals hundreds of miles high. These aren't just plumes, they're cosmic fireworks, blasting from fractures near the moon's south pole like a network of frozen volcanoes. When Cassini first spotted them in 2005, scientists were floored. No one expected this tiny moon, barely 300 miles wide, to be one of the most geologically active places in the solar system. What makes these geysers extraordinary isn't just their beauty, it's what they carry. As Cassini dove through the plumes, its instruments detected a cocktail of organic molecules, salts, and even silica nanoparticles, the kind that form in hot water interacting with rock. Together, these ingredients paint a picture of a hidden ocean, possibly global, sloshing beneath Enceladus's icy crust. And here's the kicker: where there's liquid water, energy, and organic chemistry, there's potential for life. The mechanics behind these eruptions are just as mind-bending. Unlike Earth's geysers powered by volcanic heat, Enceladus's plumes likely stem from tidal forces. As the moon orbits Saturn, the planet's gravity stretches and squeezes it like a stress ball, generating enough friction to keep the subsurface ocean liquid. The pressure builds until water bursts through cracks in the ice, carrying traces of the ocean's secrets into space. Some researchers believe these fractures act like nozzles, accelerating the vapor to speeds over 1,000 miles per hour, fast enough to escape Enceladus's weak gravity and feed Saturn's faint outer E-ring. Cassini's most daring move came in 2015, when it skimmed just 30 miles above the moon's surface, directly sampling the plumes. The spacecraft tasted molecular hydrogen, a gas often produced when water reacts with rock in hydrothermal vents, the very environments where life might have begun on Earth. It's a tantalizing parallel, suggesting Enceladus's ocean floor could harbor hot springs teeming with chemical energy. Yet the biggest question remains unanswered: is anything alive in those dark, salty depths? Future missions aim to return with more sensitive instruments, perhaps even a submarine drone to melt through the ice. For now, Enceladus stands as a glittering enigma, a frozen moon with a fiery heart, proving that even the smallest worlds can hold the grandest possibilities. If Earth's water cycle had a cosmic cousin, it would live on Titan. Saturn's largest moon boasts a hydrologic system so eerily familiar yet utterly alien, where rivers carve valleys, clouds drizzle rain, and lakes stretch across the landscape. But here's the twist: Titan's cycle runs on methane. At -180 degrees Celsius, this moon is so cold that water freezes harder than granite, while methane and ethane take center stage as the working liquids of its weather. Picture a world where gasoline flows like water, where raindrops the size of peas fall in slow motion, and where shorelines aren't edged with sand but with organic sludge. Titan's methane cycle kicks off high in its thick, nitrogen-rich atmosphere, where sunlight breaks apart methane molecules, triggering complex chemical reactions that form smog like haze. This haze coalesces into methane clouds, which drift until they unleash downpours onto the icy surface below. Radar maps from Cassini revealed sprawling river networks, some stretching hundreds of miles, etched by liquid methane winding its way toward low-lying basins. Near Titan's poles, these basins expand into vast lakes, some larger than North America's Great Lakes, filled not with water but with liquid hydrocarbons. One Kraken mare holds enough methane and ethane to drown Earth's entire oil reserves 11 times over. But what keeps this cycle going? Enter cryovolcanoes, Titan's icy answer to geysers. These frozen fountains don't spew lava. They erupt slushy mixtures of water, ammonia, and methane, replenishing the moon's atmospheric methane like a planetary-scale recycling plant. Some scientists argue these eruptions are Titan's way of venting heat from its subsurface ocean, a hidden sea of liquid water that might slosh beneath its crust. The methane doesn't just sit there either. Sunlight slowly converts it into more complex organic compounds, which snow back onto the surface as a sticky, tar-like rain. For astrobiologists, Titan is a test tube for life's possibilities. Earth's water-based chemistry is just one flavor of biology. Titan's methane dance hints at alternatives. Its dunes made of plastic-like grains and its lakes swirling with prebiotic molecules showcase how life's building blocks might assemble without a drop of liquid water. Even the moon's thick atmosphere, rich in nitrogen and carbon, mirrors the primordial conditions of early Earth. If life exists here, it wouldn't breathe oxygen. It might inhale hydrogen or metabolize acetylene, thriving in conditions that would kill terrestrial organisms instantly. Yet Titan's greatest lesson isn't about life, it's about persistence. Despite the cold, the darkness, and the chemical chaos, this moon has maintained its methane cycle for billions of years. It's a reminder that nature's processes aren't bound to Earth-like conditions, and that the universe has a knack for reinventing the familiar in the most unexpected places. Every few decades, Saturn unleashes a meteorological monster, a storm so vast it wraps around the entire planet like a cosmic belt. These are the great white spots, tempests of ammonia, ice, and hydrogen that erupt with the fury of 1,000 earthly hurricanes, bright enough to be seen by backyard telescopes across the solar system. But unlike the predictable thunderstorms of our world, these megastorms operate on a timescale that feels almost geological, appearing roughly every 20 to 30 years like clockwork. The last one, in 2010, stretched over 190,000 miles, wide enough to swallow Earth 15 times over, and raged for nearly 200 days before dissipating into Saturn's golden haze. What triggers these apocalyptic events? The leading theory points to Saturn's seasons, which last over 7 Earth years, each due to the planet's tilted axis. As summer arrives in the northern hemisphere, sunlight penetrates deeper into the atmosphere, warming layers of water vapor trapped beneath heavier hydrogen and helium. This creates a colossal updraft, like a planetary-scale elevator, hurling moist air upward until it freezes into towering ammonia clouds, the storm's signature white spot. But here's the catch: these storms don't erupt at random. They're synchronized with Saturn's orbit, always appearing when the planet's northern hemisphere tilts maximally toward the Sun, hinting at a celestial rhythm we've only begun to decode. Beneath the seasonal explanation lies an even deeper mystery: Saturn's own internal furnace. Unlike Earth, where storms draw energy from the Sun, Saturn radiates 2.5 times more heat than it receives from sunlight, a leftover from its violent formation 4.5 billion years ago. Some scientists believe this excess heat fuels the storms, bubbling up through layers of metallic hydrogen and triggering atmospheric upheaval. Others speculate that helium rain, droplets of helium condensing and falling like molten pearls through the hydrogen ocean, releases latent heat as it descends, destabilizing the atmosphere like a lid on a boiling pot. The Great White Spot of 2010 offered a rare clue. As it churned, Cassini detected radio bursts matching Earth like lightning, but with a shocking twist. These bolts were 10,000 times stronger than anything on our planet, concentrated in hotspots that migrated west at over 200 miles per hour. Even stranger, the storm's tail curled into a swirling vortex larger than Jupiter's Great Red Spot, a secondary storm that outlasted the main event by years. It's as if Saturn's atmosphere remembers these cataclysms, carrying their scars long after the skies calm. What makes these megastorms truly humbling is their impermanence. Unlike Jupiter's centuries-old cyclones, Saturn's great white spots are ephemeral cosmic fireworks that flare up, dominate the planet, then vanish without a trace. They're a reminder that even giants have moods, and that the universe reserves its most spectacular shows for those patient enough to wait. Even Saturn's frigid moons have a sense of humor, or at least the universe does. On the surfaces of Mimas and Tethys, two of the planet's most unassuming satellites, infrared cameras revealed something bizarre. Thermal maps shaped uncannily like Pac-Man, the classic video game icon mid-chomp. These aren't artistic coincidences. They're blazing hot anomalies with temperatures soaring 30 degrees Fahrenheit higher than the surrounding terrain. Their sharp, wedge-shaped boundaries defying everything we know about how heat disperses in airless worlds. The first Pac-Man appeared on Mimas in 2010, a cosmic joke hiding in plain sight. This moon, already famous for its Death Star-like crater, now had a second pop culture claim to fame. But the real shock came when Cassini spotted an identical pattern on Tethys, same V-shaped heat signature, same eerie precision. Two moons, one cosmic inside joke. Scientists quickly ruled out coincidence. Something fundamental was baking these moons in such geometrically perfect ways. The leading suspect, electrons, not just any electrons, but high-energy particles trapped in Saturn's magnetic field, raining down on the moon's surfaces like a relentless cosmic sandblaster. As these charged particles slam into the icy surfaces, they disrupt the crystalline structure of the ice, converting it into a more compact amorphous form. This process, called sputtering, releases heat, creating localized hotspots. But here's the curveball. Saturn's magnetic field channels these particles toward the moon's leading hemispheres, the sides that face forward as they orbit, focusing the bombardment into a tight, wedge-shaped zone. The result, a thermal Pac-Man eternally gobbling its way through the frozen landscape. Yet there's another twist. Some researchers argue internal heating could be at play, especially for Tethys. Its orbital resonance with neighboring moons might generate tidal friction, warming its core enough to create subtle heat plumes that rise toward the surface. If these plumes interacted with the electron bombardment, they could sharpen the thermal contrast, sculpting that iconic V shape. It's a cosmic collaboration, external forces and internal whispers working together to etch video game nostalgia onto celestial bodies. What makes these Pac-Man patterns truly mind-bending isn't just their shape, but their persistence. On airless moons with no atmosphere to redistribute heat, these anomalies can last for millennia, silent monuments to the invisible forces shaping our solar system. And they're more than just curiosities, they're roadmaps. By studying how energy flows on these moons, we're unraveling the secrets of Saturn's magnetosphere, the behavior of charged particles, and even the subterranean oceans that might lurk beneath their icy shells. So the next time you glance at Saturn, remember, hidden in its orbit are worlds where science and whimsy collide, where the cold vacuum of space pays homage to 8-bit arcade legends. It's a reminder that the universe doesn't just follow rules, it plays games, and sometimes the high score is a discovery that makes us smile. Tucked inside Saturn's glittering rings, there's a moon so small you could walk across it in under an hour, yet its impact is anything but modest. Meet Daphnis, the 8-kilometer-wide wavemaker, a celestial David among Goliaths that carves its legacy not through size but through sheer gravitational mischief. Orbiting snugly within the 350-kilometer-wide Keeler gap in Saturn's ring, This unassuming moon doesn't just drift passively, it conducts a silent symphony of chaos, sculpting ripples in the rings so precise they look like grooves on a vinyl record. What makes Daphnis extraordinary isn't just its location, it's the physics ballet it performs daily. As the moon glides along its path, its gravity tugs at the icy particles flanking the gap, pushing them outward in rhythmic waves that tower up to 1.5 kilometers high. These aren't static features, they spiral behind Daphnis like the wake of a speedboat, their peaks and troughs frozen in motion by Cassini's cameras. The closer you look, the wilder it gets. The waves actually curve, bending vertically as Daphnis' slightly inclined orbit drags ring material up and down, creating a 3D ripple effect unlike anything else in the solar system. But here's the twist, Daphnis isn't just rearranging ice, it's revealing secrets about Saturn's hidden architecture. The moon's gravitational dance has exposed faint, dusty ringlets tucked within the Keeler gap, strands so tenuous they'd vanish without Daphnis' influence to herd them. Some scientists believe these strands might be debris from impacts on Daphnis itself, tiny fragments knocked loose by meteoroids and captured by the gap's strange dynamics. Others speculate they're evidence of even smaller, unseen moonlets, their presence betrayed only by the way Daphnis' waves occasionally stutter, as if something invisible is tugging back. And then there's the kicker, Daphnis isn't just a sculptor, it's a prisoner. The Keeler gap exists because of orbital resonance, a gravitational no-man's land where particles are either ejected or swallowed by the moon's influence over time. Yet Daphnis itself is trapped there, its path locked in place by the cumulative gravity of the rings it perturbs. It's a cosmic paradox, the wavemaker can't escape the very waves it creates. The most breathtaking detail, this entire spectacle is ephemeral. Those waves aren't permanent fixtures, they're fleeting artworks, dissolving and reforming as Daphnis continues its endless lap. In 1,000,000 years, the patterns will be unrecognizable. In 1,000,000,000, the rings themselves may fade. But for now, we're privileged witnesses to a show of celestial mechanics where even the tiniest actor can bend the universe to its will, proving that in Saturn's rings, size matters far less than gravitational flair. Saturn's F-ring isn't just a ring, it's a cosmic crime scene, a twisted trail of icy evidence left by gravitational heists happening in real time. Unlike the orderly bands of Saturn's main rings, this narrow ribbon of ice and dust rides like a living thing, its braids, kinks, and clumps morphing daily under the invisible hands of two rogue moons, Prometheus and Pandora. These so-called shepherd moons don't gently guide the ring's particles, they bully them, yanking strands of ice into bizarre shapes that defy celestial etiquette. Prometheus, the larger of the two troublemakers, is the ring's prime suspect. Every 17 hours, this potato-shaped moon plunges into the F-ring's inner edge, its gravity carving out channels and dragging icy material behind it like a snowplow. But here's the twist, Prometheus's orbit isn't perfectly circular. It wobbles, ensuring each dive into the ring happens at a slightly different angle. The result, a series of stolen ice trails that overlap over time, weaving the ring's particles into braids so intricate they resemble a frozen Celtic knot. Pandora, orbiting just outside the F-ring, plays the chaotic counterpoint. While Prometheus steals material inward, Pandora's gravity tugs outward, stretching the ring's debris into sharp, kinked loops. Sometimes these opposing forces collide literally. When Prometheus's gravitational pull gets too aggressive, it can yank entire clumps of ice free, creating transient mini-moons that briefly orbit before being torn apart by tidal forces. Cassini once caught Prometheus mid-climb, its gravity sculpting a perfect spiral arm in the ring, a frozen whirlpool spinning wildly out of control. The real magic lies in the timescales. These braids aren't static artworks, they're fleeting performances. Some kinks unravel within days, others linger for months. The F-ring's entire structure can flip from smooth to snarled in weeks, a celestial loom where threads are constantly woven and frayed. Scientists even suspect smaller, unseen moonlets lurk within the ring itself, their microgravity adding another layer of chaos to the mix. What makes the F-ring truly astonishing is its defiance of expectations. Rings should be sedate, orderly places where particles follow predictable paths. Instead, Saturn's outermost major ring is a hive of anarchy, a place where gravity doesn't shepherd, it sculpts, destroys, and reinvents. Every braid is a lesson in orbital mechanics, every kink a reminder that even in the vacuum of space, nothing ever stays still. Hidden within Saturn's rings are the solar system's shyest architects, tiny moonlets so small they've never been seen directly, yet they leave behind cosmic graffiti so vivid it betrays their presence. These are the propeller moonlets, chunks of ice and rock likely no larger than a football stadium, carving bizarre, blade-like shapes into the ring material as they orbit. Cassini didn't spot them with cameras. It caught them red-handed by their wakes, pairs of delicate, S-shaped gaps stretching dozens of miles across the rings, like the swirls left behind by a boat's propeller churning through water. These propeller shapes are more than just curiosities, they're frozen snapshots of moon formation in action. Each gap forms when a moonlet's gravity tugs at the surrounding ring particles, clearing a path on either side of its orbit. The larger the moonlet, the more dramatic the disturbance. Some propellers, like the one nicknamed Blériot after the pioneering aviator, stretch over 250 miles long, suggesting moonlets up to half a mile wide lurking beneath the ring's shimmering surface. But here's the twist, these moonlets aren't just passively drifting. They're migrant workers, their orbits shifting over time as they interact with the rings and larger moons, leaving behind trails that curve and twist like cosmic fingerprints. The real revelation came when scientists realized these moonlets might be frozen embryos, failed moons that never grew large enough to break free from the rings. In Saturn's ancient past, countless chunks of ice and rock collided and stuck together, some snowballing into full-fledged moons like Enceladus or Titan. Others, trapped too close to Saturn's gravitational influence, were torn apart before they could mature. The propeller moonlets could be the survivors of that violent era, remnants of a process that's still happening today. Cassini even spotted fresh propellers appearing and vanishing over its 13-year mission, hinting at an ongoing dance of creation and destruction. What makes these moonlets truly extraordinary is how they blur the line between ring and moon. Most planets separate their rings and satellites into neat categories, but Saturn's system is fluid, a place where tiny moonlets coalesce from ring material, only to be shredded back into debris when they stray too close to the planet's gravity. Some researchers believe the propellers could be the missing link, showing how planets grow their moons from the raw material of their rings. Others speculate they're evidence of a hidden population of mini-moons, too small to spot directly but numerous enough to sculpt the rings from within. For now, the propeller moonlets remain out of reach, their full stories locked in data Cassini gathered years ago. But their legacy lingers in every ripple and gap, a reminder that even the tiniest objects can leave the grandest marks, and that Saturn's rings aren't just a static masterpiece, but a living, evolving workshop where moons are born and broken in a cycle as old as the solar system itself. Saturn's rings might be the solar system's most beautiful wreckage, a glittering debris field left behind by a moon that dared to wander too close. Picture this, a world several hundred miles wide, perhaps as large as Titan, spiraling inward over millions of years until Saturn's gravity wrenched it apart in a cataclysm so violent, its remains were pulverized into the icy shards we see today. This is the missing moon theory, and it's not just poetic speculation. The chemistry of the rings holds clues. They're 99% pure water ice, a composition that matches Saturn's inner moons almost perfectly, as if they were all carved from the same cosmic block. But the real smoking gun lies in the ring's orbits. Most of Saturn's major rings sit inside what's called the Roche limit. the point where a moon's self-gravity can no longer resist the tidal forces of the planet. Beyond this boundary, moons hold their shape. Inside it, they're doomed to splinter. The math is chillingly precise. A moon venturing inside this zone would stretch like taffy, its near side pulled harder than its far side until the difference literally tore it apart. Simulations show the fragments would initially form a dense, chaotic disk, but over time, collisions would grind them down into the flat, orderly rings we see now. Yet the story isn't that simple. Some rings, like the ghostly D ring closest to Saturn, are tinted reddish-brown, laced with organic compounds and silicates, materials more common in the outer solar system. This suggests the original moon wasn't just a ball of ice. It might have harbored a rocky core which shattered along with the rest. The faintest rings could even be fallout from that disaster, lingering traces of heavier material that didn't fully mix with the ice. Then there's the curious case of the gaps. Saturn's rings aren't uniform. They're striped with empty spaces like grooves on a record. Some, like the Cassini division, are carved by resonances with nearby moons' Mima's gravity, for instance, clears particles from its orbital path like a cosmic plow. But others defy explanation. The sharp edges of the Inca gap, for example, are too precise to be accidental. Could these voids be gravitational echoes of the missing moon's demise? Some scientists propose that as the moon fractured, its largest chunks, doomed proto-moonlets, left behind temporary wakes that herded ring material into bands, their gravity sculpting gaps that persisted long after they were ground to dust. The most haunting detail, this drama might still be unfolding. The rings are young by cosmic standards, perhaps just 100 million years old, a blink compared to Saturn's 4.5 billion year history. That means if the missing moon met its end during the age of dinosaurs, its ghost still lingers in those icy particles, a testament to the brutal ballet of gravity. And if ring rain continues draining material at its current rate, Saturn's masterpiece may vanish entirely in another 300 million years, a fleeting spectacle in the grand timeline of the solar system, reminding us that even the grandest celestial wonders are born from chaos and destined to fade. Far beyond Saturn's dazzling main rings lies a phantom, a ring so vast it defies imagination, stretching into the darkness like a cosmic tire around the planet. This is the Phoebe ring, a faint band of dust so enormous it could hold 1 billion Earths, tilted at a dramatic 27-degree angle to Saturn's equator. Unlike the icy brilliance of the inner rings, this one is dark, almost invisible, woven from particles as black as charcoal. And at its heart sits its architect, Phoebe, a rogue moon barreling backward around Saturn, its cratered surface spewing debris like a celestial coal mine in overdrive. The discovery of this shadowy giant came not from telescopes peering through eyepieces, but from an instrument designed to sense heat. In 2009, NASA Spitzer Space Telescope, tuned to detect infrared radiation, spotted an eerie glow around Saturn, a subtle warmth emitted by dust particles too sparse to reflect sunlight. The ring's dimensions were staggering. From inner edge to outer, it spans roughly 7 million miles, far enough to swallow Saturn's entire inner moon system with room to spare. Yet its material is whisper-thin. If you stood inside it, you'd need a flashlight to see the motes drifting around you. Phoebe's role in this drama is unmistakable. This moon, barely 200 kilometers wide, is a cosmic misfit. While most of Saturn's moons orbit neatly along the planet's equatorial plane, Phoebe races in the opposite direction, a telltale sign it was captured from the outer solar system. Its surface, pocked by ancient impacts, is coated in dark organic compounds, the kind found on distant Kuiper belt objects. Every time a meteoroid strikes Phoebe, it blasts this sooty material into space, where Saturn's gravity corrals it into the sprawling ring we see today. But the Phoebe ring isn't just a curiosity, it's an artist. Scientists believe its particles are the cosmic paintbrushes behind Iapetus's two-toned face. As the ring's dark dust spirals inward, some of it collides with Iapetus's leading hemisphere, the side that plows forward as the moon orbits. Over eons, this steady rain of carbon-rich particles has stained Iapetus's once pristine ice into a tar-black canvas, while its trailing hemisphere remains blindingly bright. The process is a masterclass in celestial mechanics, a distant moon's debris altering the appearance of another world millions of miles away, the strangest twist. This ring might be a time capsule. Phoebe's composition suggests it originated in the outer solar system, where primordial building blocks have lingered unchanged for billions of years. By studying the Phoebe ring, we're effectively sampling material from the Kuiper belt without sending a probe, a free delivery of cosmic artifacts from the solar system's darkest frontiers. Yet for all its grandeur, the Phoebe ring is a ghostly enigma. Unlike Saturn's main rings, which sparkle in sunlight, this one is a shadow play, visible only when backlit by the infrared glow of its own heat. Its particles don't orbit forever either. Drawn inward by subtle forces, they eventually spiral toward Saturn, where they may seed the upper atmosphere with exotic chemicals or even contribute to the planet's mysterious dark polar hexagon. What makes the Phoebe ring truly humbling is its scale. A structure this vast shouldn't exist, not so faint, not so tilted, not so defiantly dark. Yet there it is, a testament to the chaos of celestial capture and the slow-motion artistry of gravity. It's a reminder that even in the well-mapped realms of our solar system, the universe still hangs its darkest masterpieces where we least expect them. If you think Saturn's moons can't get any weirder, meet Mimas, the solar system's ultimate cosmic doppelganger. This moon doesn't just resemble the Death Star from Star Wars, it puts the fictional superweapon to shame. One glance at its surface reveals why. A crater so colossal, it covers nearly a third of the moon's face, with a central peak jutting 4 miles high, like a bull's eye left by the universe's most reckless sharpshooter. Named Herschel after the astronomer who discovered Mimas, this impact scar stretches 80 miles wide, so deep that its floor sinks 6 kilometers below the crater's rim. For scale, if Earth had a crater proportionally this size, it would dwarf the Grand Canyon stretching from New York to Chicago. The miracle isn't just the crater's size, it's that Mimas survived the hit at all. The impact that carved Herschel would have released enough energy to vaporize most moons, cracking them open like eggs. Yet Mimas held together, albeit with fractures spider-webbing halfway around its body on the opposite side, as if the shockwaves nearly tore it apart in slow motion. Scientists estimate the collision released 1 billion times more energy than the asteroid that wiped out the dinosaurs, a cataclysm so violent it should have shattered Mimas into Saturn's rings. So why didn't it? The answer might lie beneath the moon's icy shell. Recent data from Cassini's flybys revealed something odd. Mimas wobbles, not much, just a few hundred meters, but enough to hint that its rigid exterior might hide a secret. Some researchers argue this oscillation points to a global ocean sloshing beneath 24 kilometers of ice, a liquid layer acting like a shock absorber that redistributed the impact's energy. Others disagree, noting the moon's surface lacks the telltale cracks and geysers seen on Enceladus, where an underground ocean regularly erupts into space. Instead, they propose Mimas might harbor a football-shaped core, its uneven density causing the wobble. But here's the twist that reignited the debate. Computer simulations show Herschel's formation would have melted so much ice that any subsurface ocean should have frozen solid within 10 million years. Yet if Mimas has no ocean today, why does its interior still seem oddly flexible? One daring theory suggests tidal forces from Saturn might still be kneading the moon's insides, generating enough heat to keep pockets of slushy, half-melted ice trapped beneath the crust. Another wild idea, the impact that made Herschel actually created a temporary ocean that later refroze, leaving behind a fossilized layer of warm, deformable ice that still softens the moon's movements. The stakes are higher than a sci-fi comparison. If Mimas does conceal an ocean, it rewrites the rules for where life could exist in our solar system. This moon is tiny, just 250 miles wide, with no signs of geologic activity. Yet if even a frozen, battered world like Mimas can hide liquid water, then oceans might lurk in the unlikeliest places. For now, Herschel keeps its secrets, a silent sentinel with a face that launched 1,000 theories. Whether it's whispering clues about hidden seas or simply flaunting the universe's sense of humor, one thing's certain: in Saturn's orbit, even the scars have stories to tell. Deep beneath the icy crust of Enceladus, something is stirring, and the evidence is written in scars across its south pole. While most moons this small should be frozen solid, Enceladus betrays its secret the moment you glance at its southern hemisphere. A tangled web of fractures nicknamed tiger stripes, where temperatures soar to a shocking -135 degrees Fahrenheit. That might sound cold by Earth standards, but for the outer solar system, it's practically tropical, nearly 100 degrees warmer than the surrounding terrain. These cracks aren't just surface blemishes, they're the fiery fingerprints of a moon with a beating heart, spewing plumes of water vapor and organic material into space like a cosmic pressure valve. The heat radiating from these grooves was one of Cassini's most baffling discoveries. Conventional wisdom said a moon barely 300 miles wide, orbiting 1 billion miles from the Sun, should be geologically dead. Yet infrared scans revealed the tiger stripes glowing with unexpected warmth, concentrated along their length like smoldering embers. The explanation: tidal heating. As Enceladus orbits Saturn, the planet's gravity stretches and compresses the moon, generating enough internal friction to keep a global ocean liquid beneath the ice. But at the South Pole, this process goes into overdrive. The ice crust there is thinner, possibly as little as 3 miles thick in places, allowing heat from the ocean below to bleed through, softening the ice and creating the perfect conditions for those dramatic eruptions. What makes these plumes truly extraordinary is their cargo. Cassini's instruments detected sodium salts, silica nanoparticles, and a cocktail of organic molecules, including methane, carbon dioxide, and traces of complex hydrocarbons. These aren't just random chemicals, they're the building blocks of life as we know it. The silica particles, in particular, tell a tantalizing tale. On Earth, they're produced when hot water interacts with rock, typically in hydrothermal vents on the ocean floor. If the same process is happening beneath Enceladus's ice, it could mean the moon's hidden sea isn't just warm, it's interacting with a rocky core, leaching minerals and energy into the water like a cosmic tea steeping in the dark. The implications are staggering. On our own planet, hydrothermal vents are oases of life, hosting entire ecosystems that thrive without sunlight, fueled by chemical energy. If Enceladus has similar vents, its ocean could be doing more than just existing. It might be brewing. Some researchers speculate that the plumes themselves could carry microbial hitchhickers, ejecting potential life into space where future probes might detect it. Others caution that the moon's chemistry, while promising, might lack the stability for life to take hold. But one thing's certain: Enceladus's overheated south pole is more than a geological oddity. It's a beacon, drawing us toward the possibility that we're not alone in the universe. The tiger stripes themselves add another layer of mystery. Unlike random cracks, these fractures are eerily parallel, spaced about 21 miles apart and stretching nearly 80 miles long. Their uniformity hints at a precise mechanism, perhaps stresses in the ice shell caused by the moon's wobbling orbit, or the ebb and flow of the subsurface ocean beneath. Some models suggest the stripes act like tectonic faults, sliding past each other as the ice flexes, generating enough heat to keep the vents active. Others propose that the plumes actually stabilize the cracks, with erupting vapor acting like a lubricant that prevents them from sealing shut. But the most haunting question isn't how the tiger stripes formed, it's why they're only at the South Pole. If Enceladus has a global ocean, why isn't the entire moon crackling with geysers? The answer might lie in asymmetry. Saturn's gravity could be focusing tidal forces disproportionately on the southern hemisphere, or the ice shell might be uneven, with the South Pole's thinner crust acting like a weak spot in a balloon. There's even a chance the moon's interior is lopsided, with heat concentrated near one pole due to quirks in its core. Whatever the reason, the result is a moon that wears its secrets on its sleeve, or rather, its south pole, offering us a front-row seat to the dynamic interplay of ice, water, and energy. Enceladus isn't just another icy world, it's a testament to the ingenuity of nature, a place where heat, water, and chemistry conspire to create an environment that, against all odds, might just nurture life. And as the plumes from those tiger stripes continue to fountain into space, they carry with them an invitation to look closer, to dig deeper, and to wonder what other surprises this tiny moon might be hiding beneath its frozen shell. Saturn's polar hexagon is more than just a geometric marvel, it's a thermal rebel, radiating heat where scientists least expected it. High above the planet's cloud tops, where temperatures should plummet to bone-chilling lows, infrared scans reveal the hexagon's upper reaches glowing with an eerie warmth. This isn't just a minor anomaly, it's a full-blown atmospheric mutiny, defying every model of how planetary weather systems behave. The hexagon's edges, sharp enough to rival a laser-cut gem, coincide with jets of air screaming at 320 miles per hour, yet the heat signature hovers dozens of miles above these winds, like a fever with no clear source. What makes this warmth so baffling is its disconnect from the storm below. On Earth, heat in weather systems typically comes from below, warm oceans fueling hurricanes or sun-baked land spawning thunderstorms. Saturn's hexagon flips that logic on its head. The warmth isn't rising from the depths, it's being generated aloft, possibly by energy cascading downward from the planet's stratosphere. Some researchers speculate that gravity waves' massive ripples in the atmosphere, not to be confused with gravitational waves in space, are channeling energy from lower altitudes upward, where it crashes like an invisible tide and dissipates as heat. Others propose that the hexagon's sheer stability creates a sort of atmospheric cap, trapping energy like a lid on a simmering pot. Then there's the depth factor. While most storms churn within a narrow layer of a planet's atmosphere, Saturn's hexagon appears to be a stacked beast, with roots plunging hundreds of miles below the cloud tops. Cassini's gravity measurements suggest the hexagon's rotation syncs with Saturn's deep interior, implying this isn't just a skin-deep pattern but a phenomenon anchored to the planet's very core. That linkage might explain the heat anomaly. If the hexagon is tapping into Saturn's internal energy reserves, it could be venting that heat upward through its towering walls, like steam escaping through cracks in a geothermal field. The kicker: this heat might be the hexagon's secret to longevity. Most planetary storms dissipate when they lose energy to friction or cold surroundings. But if the hexagon is self-heating, recycling energy from Saturn's depths or its own atmospheric mechanics, it could sustain itself indefinitely. It's a cosmic perpetual motion machine, a six-sided engine that defies the universal trend toward disorder. And that raises a tantalizing question. If warmth aloft is the key to this storm's immortality, could similar mechanisms be at work in other planets' polar vortices, even Earth? For now, the hexagon keeps its secrets, a towering enigma where geometry, heat, and wind conspire to create something that shouldn't exist. It's a reminder that Saturn doesn't just challenge our expectations, it rewrites them, one warm, six-sided mystery at a time. Saturn's rings aren't just flat, featureless sheets, they're cosmic origami, folded into towering peaks that rival Earth's greatest mountains. Hidden among the countless icy particles are vertical structures stretching 2.5 miles high, invisible most of the time but revealed in dramatic fashion during Saturn's equinoxes. When sunlight hits the ring's edge-on, these gargantuan waves cast shadows so long and sharp, they look like dark claws raking across the ring plane. It's as if Saturn, for a brief moment, pulls back the curtain to show off its most jaw-dropping ring sculpture. These ring mountains aren't solid landforms, they're waves frozen in motion, ripples of densely packed ice created by gravity's invisible hand. Their origin story reads like a celestial tug of war. Some form when tiny moonlets like Daphnes plow through the rings, stirring up material like a speedboat carving wakes in a lake. Others emerge from gravitational resonances with larger moons, where rhythmic tugs from bodies like Mimas or Pan compress ring particles into towering crests and troughs. The most astonishing part, these structures don't collapse under their own weight. Without friction or wind to erode them, they persist for decades, their perfect shapes preserved in the vacuum of space. The equinox reveal is a fleeting spectacle. Twice during Saturn's 29-year orbit, the Sun aligns perfectly with the ring plane, illuminating these vertical labyrinths in sharp relief. Shadows stretch hundreds of miles, turning the rings into a topographical map of hidden upheavals. Cassini's cameras captured this phenomenon in 2009, spotting shadows so crisp they could be measured down to the meter. One particularly dramatic wave, spawned by the moon Prometheus, cast a shadow revealing a slope steeper than the north face of the Eiger, but the true marvel lies in the physics. These waves don't just rise, they spiral. As ring particles orbit Saturn, their collective motion twists the vertical structures into corkscrews like frozen tsunamis winding through the rings. Some even resemble the grooves of a vinyl record, their precise spacing betraying the gravitational harmonies that birthed them. And here's the kicker, these formations aren't static. Over time, they drift, their shapes evolving as the moons that influence them shift in their orbits. What makes these mountains even more extraordinary is their impermanence. Unlike Earth's peaks forged over millennia, Saturn's ring topography can change in weeks. A passing moonlet might spawn a new range, while another's gravitational nudge could flatten an ancient wave. It's a dynamic, ever-changing landscape where the only constant is motion, a reminder that even the most delicate-looking features in our solar system can hide staggering scale and complexity. The next time you gaze at Saturn's rings, remember, you're not just seeing a flat disk, you're looking at a three-dimensional masterpiece with valleys and peaks lurking in plain sight, waiting for the perfect light to unveil their secrets. And somewhere in those shadows, there's a story still being written, one where gravity is the artist and ice is its canvas. Titan's methane lakes aren't just puddles, they're alien seas, deep enough to swallow skyscrapers and dynamic enough to rewrite the rules of chemistry. Take Kraken Mare, the largest of these liquid reservoirs, sprawling over 150,000 square miles with depths exceeding 1,000 feet. That's deeper than Lake Superior, but instead of water, it's brimming with a cocktail of methane and ethane, hydrocarbons that would be gases on Earth, but here, in Titan's cryogenic embrace, flow like frigid gasoline. Radar measurements from Cassini pierced the lake's murky surface, revealing submerged canyons and islands, hinting at a topography as complex as any terrestrial coastline. What's truly startling is how these lakes breathe with the seasons. Titan's year lasts 29 Earth years, and as its northern hemisphere tilts toward the sun, methane evaporates, forming thick clouds that drift southward before raining down to fill lakes there. Cassini witnessed this slow-motion hydrologic cycle in action, entire basins shrinking by meters during Titan summer, only to refill decades later. But here's the twist, the lakes aren't pure methane. Spectral data detected traces of ethylene, propane, and even hydrogen cyanide, a toxic compound that, in Titan's cold, could act as a building block for more complex molecules. Some shorelines even show bathtub rings of benzene and other organics, residue from evaporated liquids that might concentrate probiotic ingredients like a cosmic reduction source. Now imagine life swimming in those depths. Earth's extremophiles thrive near underwater volcanoes, metabolizing chemicals instead of sunlight. Titan's lakes could host analogous organisms, not water-based but liquid methane-based, with cell membranes forged from flexible acrylonitrile instead of lipids. These hypothetical azotosomes could theoretically function at -180 degrees Celsius, their biochemistry slowed to a glacial pace. The energy source, acetylene raining from the sky, reacting with hydrogen in the lakes to release energy, a process lab experiments have shown is chemically plausible. Yet the lakes guard their secrets fiercely. Their surfaces are eerily smooth, with waves rarely taller than a few centimeters. Titan's thick atmosphere and low gravity suppress ripples. But beneath that glassy veneer, currents might swirl, driven by tides from Saturn's gravity or seasonal temperature shifts. Some models suggest methane waterfalls could cascade into underground aquifers, while others propose cryovolcanic vents pumping fresh hydrocarbons into the depths. The most tantalizing clue lies in Ligeia Mare, Titan's second largest sea. In 2013, Cassini spotted a mysterious feature dubbed Magic Island, a bright splotch that appeared and vanished within weeks. Was it a floating iceberg of frozen hydrocarbons? A surge of nitrogen bubbles from the seabed, or something far stranger, a hint that Titan's lakes are even more alive than we dared imagine. For now, these methane seas remain the solar system's most enigmatic bodies of liquid, a place where chemistry dances on the edge of biology, and where every ripple, real or imagined, could rewrite our understanding of life's possibilities. Titan's lakes hold a secret that defies logic: phantom islands that flicker in and out of existence like cosmic mirages. These so-called magic islands first teased scientists in 2013, when Cassini's radar glimpsed a bright splotch in Ligeia Mare, Titan's second largest sea. Within weeks, it vanished without a trace. Then, like a celestial prankster, the phenomenon repeated flashes of brightness appearing and dissolving across multiple passes, some lasting just days, others lingering for months. These weren't camera glitches or data artifacts. They were real, unresolved mysteries bobbing in an alien ocean of liquid methane. So what could possibly explain these ghostly features? One leading theory points to nitrogen bubbles, explosions of gas erupting from the lakebed like champagne fizz. Titan's extreme cold allows nitrogen, which is normally a gas on Earth, to dissolve into the methane-ethane mix. When slight temperature changes occur, perhaps from seasonal shifts or tidal heating, the nitrogen could burst forth in bubbly plumes, creating temporary rafts of foam that scatter radar signals before popping into oblivion. Another idea suggests floating solids, icebergs of frozen organic compounds like benzene or acetylene. Unlike Earth's water ice, these wouldn't sink. Titan's slushy hydrocarbons might allow them to drift like frozen froth until they melt or dissolve. But there's a wilder possibility: waves. Normally, Titan's thick atmosphere and low gravity suppress ripples, leaving its lakes eerily smooth. Yet during windier seasons, transient waves could form, their crests reflecting radar brightly before calming back into glassy plains. Some scientists argue these aren't ordinary waves, but swarms of suspended particles. Imagine a methane lake suddenly churning with floating debris, only to settle again as currents shift. The most tantalizing theory, though, involves something far stranger: organic mush. Titan's atmosphere constantly rains complex molecules, which might clump into porous, honeycomb-like blobs. Buoyant and fragile, these could float temporarily before saturating and sinking, or even interact with the liquid methane in ways we've yet to imagine. What makes the Magic Islands so mesmerizing isn't just their mystery, it's their hint of dynamism. On a moon where everything moves at a glacial pace, these fleeting features prove that Titan's lakes are anything but stagnant. They're alive with processes we're only beginning to decode, where chemistry and physics conspire to create phenomena unseen anywhere else in the solar system. Every flicker on the radar is a reminder: even in the coldest corners of the cosmos, change is the only constant. deep within Saturn's churning depths, a storm of unimaginable luxury is brewing, one where droplets of liquid helium fall like diamonds through an ocean of metallic hydrogen. This isn't science fiction, it's a phenomenon called helium rain, and it might be the key to unlocking some of Saturn's most stubborn secrets. Picture this: under pressures millions of times greater than Earth's atmosphere and temperatures hotter than the Sun's surface, hydrogen transforms into a bizarre, shimmering metal, a fluid that conducts electricity like copper yet flows like water. And suspended in this alien sea, helium, the second lightest element, forced into a liquid state so dense it forms droplets heavy enough to plunge downward in a slow-motion deluge. This cosmic rainfall isn't just poetic, it's planetary alchemy. As helium droplets descend, they release gravitational energy, heating Saturn's interior like a nuclear furnace. Here's the twist: Saturn radiates 2.5 times more heat than it receives from the Sun, and helium rain could be the missing piece of that puzzle. Every falling droplet converts potential energy into warmth, explaining why the planet still glows with the remnants of its formation 4.5 billion years later. But the real magic happens when this rain reaches deeper layers. Helium doesn't mix easily with metallic hydrogen, so as it sinks, it strips the surrounding hydrogen of its electrons, creating a dynamic, electrically charged boundary layer. This process isn't just about temperature, it's a hidden engine that might power Saturn's mysteriously symmetrical magnetic field. Speaking of magnetic fields, Saturn's is an outlier. Most planets like Earth or Jupiter have magnetic poles roughly aligned with their rotational axis. Saturn's, however, is nearly perfect. Its north and south magnetic poles are so precisely balanced that scientists initially doubted their measurements. Helium rain could be the architect of this precision. As the droplets sink, they redistribute electrical currents in the metallic hydrogen layer, smoothing out irregularities that would otherwise tilt or warp the magnetic field. It's like a planetary scale tuning fork, with helium rain harmonizing the chaos into a symmetrical hum. Yet the plot thickens. Some models suggest this rain isn't uniform. It might fall in sporadic bursts, creating waves of heat that ripple through Saturn's interior. These thermal pulses could explain why the planet's rotation rate seems to shift over time, as measured by Cassini's radio emissions. Imagine a clock where the gears periodically expand and contract, altering the tick. That's Saturn's core, its heartbeat syncopated by the unpredictable rhythm of helium downpours. The wildest implication: this isn't just Saturn's story. Helium rain likely drenches Jupiter too, but Saturn's weaker gravity allows the phenomenon to dominate its energy budget more visibly. Studying this process gives us a backstage pass to the inner workings of gas giants across the universe, exoplanets included. Every droplet is a clue, a whisper from the depths about how planets distill their heat, shape their magnetic shields, and even influence their own winds. So the next time you gaze at Saturn's golden hue, remember, beneath those serene clouds, a storm of liquid helium is falling, rewriting the rules of planetary physics one drop at a time. And somewhere in that downpour, the universe is hiding answers to questions we've only begun to ask. Saturn's rings don't just dazzle, they defy. Unlike the flat, orderly disks we might expect, they tilt at a dramatic 27-degree angle to the planet's orbit around the Sun, a slant so pronounced it's visible from Earth with even modest telescopes. But here's the cosmic conundrum. In a universe where gravity loves to flatten things into neat planes, how does Saturn's ring system maintain this rebellious lean? The answer might lie with Titan, Saturn's largest moon, whose gravitational whispers could be the invisible hand keeping the rings permanently cocked. This tilt isn't static, it wobbles gently over time due to a phenomenon called precession, much like a spinning top slowly tracing circles as it winds down. But what's truly fascinating is the math behind it. Titan's orbit around Saturn is inclined too, and as it tugs on the rings from different angles over its 16-day trip, its gravity acts like a metronome, nudging the ring plane to match its own tilt. The numbers line up eerily well. The ring's precession rate, the speed at which their tilt wobbles, syncs almost perfectly with Titan's orbital rhythm, locking the system into a gravitational resonance that's likely persisted for billions of years. It's a celestial feedback loop where Titan's subtle pulls reinforce the ring's defiance against flattening, preserving their dramatic slant like an eternal cosmic lean. But why does any of this matter? Because this tilt isn't just a quirk, it's a time capsule. The angle of the rings holds clues to Saturn's chaotic infancy. One theory suggests the planet's core might have been jolted sideways during the solar system's violent early days, perhaps by a colossal collision or the gravitational bullying of a passing giant. Another idea points to the migration of Saturn's moons. As Titan and its siblings shifted orbits over eons, their collective gravity could have gradually torqued the entire system askew. The rings, being relatively young at perhaps 100 million years old, inherited this tilt like a family heirloom, their orientation preserving a snapshot of the planet's tumultuous past. Here's where it gets even stranger. The tilt might explain why Saturn's rings are so pristine. A steep angle exposes the rings to more sunlight, preventing ice particles from clumping too densely and helping them stay bright and reflective. It's possible that without Titan's gravitational stewardship, the rings might have collapsed or darkened long ago, yet this delicate balance is precarious. Some models suggest the tilt could be decreasing over time, as other moons like Iapetus and Rhe tug in opposing directions, their combined influence slowly eroding Titan's dominance. The real kicker, this tilt might not be unique. Exoplanets with ring systems could harbor similar dynamics, their own moons acting as cosmic stabilizers. Saturn's slanted rings, then, aren't just a visual marvel, they're a masterclass in gravitational teamwork. A reminder that even the slightest nudge from a distant moon can shape the destiny of a planet's most iconic feature. And as we peer deeper into the cosmos, that lesson might help us decode the hidden histories of worlds far beyond our own. Saturn's rings aren't just empty space between bands of ice, they're cosmic construction zones, patrolled by bizarre moons that defy every expectation of how a moon should look. Take Pan and Atlas, two of Saturn's strangest satellites, each wedged inside their own razor-thin gaps in the rings like celestial janitors sweeping up debris. These aren't your typical spherical moons. They're flattened, bulging at their equators like someone pressed a thumb into their centers while they were still soft. Pan, the innermost of the pair, orbits snugly within the 325-kilometer-wide Inca Gap, its strange shape earning it nicknames ranging from space ravioli to cosmic UFO. But this isn't just whimsy. Every ridge and valley on these moons tells a story of gravitational artistry in action. What molds a moon into a flying saucer? The answer lies in their day jobs as gap shepherds. As Pan and Atlas orbit, their gravity tugs at the icy particles along the edges of their gaps, nudging some outward and others inward, clearing a pristine lane through the chaos. But here's the catch: the rings aren't passive. Tiny particles spiral toward the moons over time, drawn by weak gravitational attraction, and instead of crashing into the surface, they smolder into a delicate dance around the equator. Over millennia, this slow-motion snowfall builds up, piling into those signature equatorial ridges. It's like a cosmic 3D printer with ring dust as the ink and gravity as the blueprint. The details get even weirder. Atlas, perched at the outer edge of the ring, takes this sculpting to extremes. Its ridge isn't just pronounced, it's disproportionately massive, making the moon look like someone glued a dinner plate to a walnut. Some scientists argue this bulge might be less about accumulated ring material and more about the moon's own fragility. Atlas's core could be porous, a loosely packed rubble pile that settled into this shape under its own weak gravity, with the ridge representing the least unstable configuration. Others suggest the moon might be actively falling apart. its equator shedding material even as new ring particles accumulate, a balancing act between construction and demolition. Then there's the mystery of the gaps themselves. The Inca gap where Pan resides isn't perfectly empty, it's threaded with faint, spiral ringlets that coil around the moon like ribbons. These aren't static decorations, they're dynamic waves generated by Pan's gravity as it plows through stray particles. Every pass creates new kinks and braids, a frozen record of the moon's orbit. Meanwhile, Atlas's domain showcases something even stranger: clumps. The faint arcs of material near its orbit hint at unseen moonlets, fragments too small to spot but large enough to leave gravitational fingerprints. It's a reminder that Saturn's rings are never truly empty, just hiding their architects in plain sight. The real magic of these gap moons lies in their impermanence. They're not ancient relics, they're works in progress. Every micron of ring dust they gather changes their shape, their mass, even their gravitational reach. In a million years, Pan's ridges might thicken into a full skirt, or Atlas could crumble under its own uneven weight. For now, they spin on, silent custodians of the ring's sharpest edges, proving that even the emptiest-looking spaces in our solar system are humming with invisible motion, and that sometimes the universe's most ingenious designs look like they were dreamed up by a pastry chef. Hidden beneath Saturn's golden clouds, a symphony of alien lightning crackles, and it doesn't just flash silently. These bolts unleash eerie radio echoes known as whistlers, spectral sounds that warp and slide down the electromagnetic spectrum like a ghostly slide whistle. First detected by Voyager in the early 1980s, these electromagnetic whispers aren't just cosmic noise. They're fingerprints of storms so powerful they dwarf anything on Earth. A single Saturnian lightning bolt can blast out 1,000,000 times more radio energy than its terrestrial counterpart, with discharges spanning hundreds of miles across. But it's the whistlers that carry the real secrets, bending through Saturn's magnetosphere like electrified ribbons, revealing paths through the planet's turbulent atmosphere that no probe could ever physically trace. What makes these signals so haunting is how they evolve. As the radio waves travel, they slice through plasma, a soup of charged particles in Saturn's magnetic field, at slightly different speeds depending on their frequency. Higher pitches race ahead while lower tones lag behind, stretching the signal into that signature descending whistle. Cassini's radio antennas caught thousands of these over 13 years, each one a breadcrumb leading back to a storm's epicenter. By triangulating their paths, scientists reconstructed a hidden map of Saturn's electrical weather, discovering that most lightning erupts in a mid-latitude band nicknamed Storm Alley, where titanic thunderheads churn for months at a time. The real shock came when researchers realized these whistlers weren't just passive echoes, they were interacting with Saturn's rings. As the radio waves skimmed the inner edge of the rings, they triggered secondary emissions, essentially making the rings sing along with the lightning. This bizarre coupling revealed something unexpected. The rings are far more electrically conductive than anyone predicted, possibly due to tiny dust particles becoming ionized by solar radiation or Saturn's own magnetic field. But the ultimate surprise was timing. Unlike Earth, where lightning strikes last microseconds, Saturn's bolts flicker for seconds, sometimes even minutes, suggesting storms of unimaginable scale. Some whistlers arrive in synchronized bursts, hinting at superbolts flashing in unison across thousands of miles, a level of coordination terrestrial storms never achieve. Others drift lazily, their distorted tones suggesting they've traversed bizarre plasma structures we've yet to fully understand. These radio ghosts do more than just dazzle. They're teaching us how planetary atmospheres generate and harness electricity. On Earth, lightning helps balance charge between the ground and ionosphere. Saturn's whistlers suggest a similar global circuit, but operating at scales we can barely fathom. A reminder that even in the realm of gas giants, the age-old dance of energy and atmosphere follows rhythms both alien and eerily familiar. Saturn isn't just a golden jewel in the night sky. It's a cosmic mood ring, shifting hues as slowly and deliberately as the turning of pages in a celestial calendar. Over its 29-year orbit, the planet's atmosphere transforms from a warm, buttery gold to cooler, bluish tones, a kaleidoscope driven by sunlight and the hidden chemistry of its upper clouds. These changes aren't random, they're tied to Saturn's seasons, each lasting roughly 7 Earth years, as the angle of sunlight striking its atmosphere shifts with the planet's tilted axis. But here's the twist: unlike Earth, where seasonal shifts mean falling leaves or blooming flowers, Saturn's transformations play out in the delicate dance of aerosols and photochemistry, painting the planet in shades we're only beginning to decode. The golden tones dominating Saturn's usual palette come from ammonia crystals high in its atmosphere, reflecting sunlight like a blanket of cosmic pollen. But as winter grips a hemisphere, temperatures plummet and stratospheric haze thins, allowing sunlight to penetrate deeper. This triggers a cascade of reactions. Ultraviolet light breaks down methane, forming hydrocarbons like acetylene and ethane. These molecules, along with nitrogen compounds, cluster into tiny particles that scatter blue light, much like Earth's sky, but on a planetary scale. Cassini's cameras captured this shift dramatically during Saturn's northern winter in the late 2000s, when the planet's north pole took on an ethereal azure tint, a stark contrast to the South's lingering gold. What's even more fascinating is the lag. Saturn's atmosphere doesn't respond instantly to seasonal changes. It breathes over years. The blues of winter don't peak until halfway through the season, as chemical processes slowly amplify the effect. Then, as spring approaches, increased solar radiation warms the stratosphere, reviving the golden haze and erasing the blue like a tide washing over sand. This hysteresis, a delay between cause and effect, reveals just how complex Saturn's atmospheric engine really is, with layers of circulation patterns moving at different speeds, each fighting for dominance. But the real wild card: storms. During its equinoxes, when sunlight strikes Saturn's equator directly, the planet has historically unleashed colossal white storms, massive upwellings of ammonia-laden air that churn the atmospheric layers like a spoon in paint. These tempests inject fresh material high into the stratosphere, temporarily resetting the color palette. The 2010 storm, for instance, left behind a splatter of white streaks that lingered for years, disrupting the usual seasonal gradient. It's a reminder that Saturn's hues aren't just passive reflections. They're a living canvas shaped as much by chaos as by rhythm, the grand takeaway. Saturn's colors aren't just pretty, they're a language. By reading them, scientists can infer wind speeds, temperature gradients, even the lifespan of atmospheric constituents. That bluish tint, it's a billboard advertising cleaner, colder air. The golden bands, they're highways of convection, ferrying heat from the depths, and every subtle shift whispers secrets about how gas giants age, evolve, and interact with the sun's fickle light. So the next time you see Saturn shining in the sky, remember, you're not just looking at a planet, you're witnessing a masterpiece in motion, painted stroke by stroke over decades by the quiet hand of celestial seasons. Saturn's rings are staging the ultimate disappearing act, not with a sudden cosmic puff, but in a slow, silent fade that's already underway. Every second, the planet's gravity tugs thousands of tons of icy material from the rings, sending it cascading into Saturn's atmosphere as ring rain. This delicate downpour, invisible to the naked eye, is draining the rings so relentlessly that scientists estimate they could vanish entirely in as little as 100 million years, a blink in cosmic time. For context, that means if the rings formed when dinosaurs still roamed Earth, they could be gone before our sun swells into a red giant. The mechanics of this vanishing act are as elegant as they are inevitable. Saturn's rings aren't solid. They're a swirling sea of ice chunks, from dust-sized grains to boulders, all orbiting in a fragile balance between gravity and momentum. But in the planet's shadow, where sunlight charges the particles, subtle forces take over. Electrically charged ice gets caught in Saturn's magnetic field lines, spiraling inward like water circling a drain. Cassini's final orbits detected this rain directly, with instruments measuring a constant drizzle enough to fill an Olympic pool every half hour. Over millennia, this adds up. The innermost rings, already the faintest, could erode first, leaving gaps that widen like unraveling seams. What's startling isn't just the ring's demise, it's the timing. Geological evidence suggests the rings might be surprisingly young, perhaps only 100 million years old. If true, we're witnessing a fleeting masterpiece, a celestial spectacle that future civilizations might never see. By the time Earth's continents merge into the next supercontinent, Saturn could appear naked to the naked eye, its golden disk stripped of its crowning glory. Yet the rings won't vanish without a trace. As they disintegrate, their material will seed Saturn's upper atmosphere with water and organic compounds, potentially altering its chemistry. Some models predict a temporary brightening of the planet's clouds as the influx of ice enhances reflectivity. Others suggest the rain could perturb atmospheric currents, subtly shifting storm patterns over eons. Even Saturn's magnetic field might feel the change as the influx of charged particles tweaks the planet's internal dynamo. For Earth-bound observers, the process will be achingly slow. Telescopes of the far future might detect the rings thinning at their edges first, like a receding hairline, before gaps fracture their continuity. The most poignant moment will come when the Cassini division. The dark band between the A and B rings widens until it swallows its surroundings, leaving behind a skeleton of what once was. Future astronomers might puzzle over ancient sketches of Saturn, wondering how humanity once glimpsed a grandeur now lost to time. But here's the cosmic irony: Saturn's rings are vanishing just as we've learned to appreciate them. Their impermanence makes them even more precious, a reminder that the universe is a stage where even the grandest sets are temporary. And somewhere in their silent reign is a lesson. Beauty isn't measured in eons, but in the lucky moment we're there to see it. From hexagonal hurricanes to diamond rain, vanishing rings to whispering lightning, Saturn has proven itself the solar system's greatest enigma, a planet where the laws of physics seem rewritten daily. We've explored 30 of its most baffling secrets: storms that outlast civilizations, moons shaped like flying saucers, lakes of liquid methane hiding phantom islands, even a ring so vast it could swallow 1 billion Earths. Each discovery peels back another layer of Saturn's mysteries, only to reveal deeper questions. How does a storm maintain perfect geometry for centuries? Why do some moons resemble crushed rubble piles while others hide global oceans? What strange chemistry unfolds in those golden clouds, painting the planet's hues like a cosmic mood ring? The true magic lies in how these puzzles intertwine. Titan's methane cycle feeds Saturn's atmosphere with organic compounds, while the Phoebe ring stains Iapetus black from millions of miles away. The rings themselves, once thought static, are caught in a celestial tug-of-war, sculpted by shepherd moons and drained by invisible rain. Even Saturn's heartbeat remains elusive, its rotation rate shifting as helium droplets fall through its metallic heart. This isn't just a planet, it's a dynamic ecosystem where every piece, from the tiniest propeller moonlet to the mightiest megastorm, plays a role in a grand celestial ballet. Yet for every answer, Saturn tosses us 3 new riddles. The hexagon's heat defies atmospheric models. Enceladus's tiger stripes erupt with chemistry ripe for life, but is anything actually there? And those fleeting spokes in the rings, after decades of study, they still vanish before we can decode them. That's the paradox of exploration. The more we learn, the humbler we become. So here's my challenge to you: which of Saturn's secrets left you utterly speechless? Was it the impossible longevity of the hexagon, or the way Mimas survived an impact that should have vaporized it? Maybe the eerie whispers of lightning in the rings, or the fact that we're watching those iconic rings fade in real time. Drop your pick in the comments, and while you're at it, look up tonight. Saturn's out there right now, glowing golden in the dark, its mysteries still spinning, still waiting. Because the universe's greatest stories aren't in textbooks, they're written in the storms of gas giants, the ice of distant moons, and the endless curiosity of those who dare to wonder.